The Technical Committee 301 Historic Sites under ISSMGE has initiated the lecture series on conservation of heritage sites with the support of Indian Geotechnical Society. Technical Committee 301 works in the area of geotechnical aspects and conservation of heritage sites. We have total 47 members around the world in this particular committee. Many of them have joined for this particular lecture. To know more about the Technical Committee 301, please visit our Technical Committee 301 website, in which you'll be able to access the online lectures, webinars, what are the future events which are going to be there in the area of conservation of heritage. Then we have also included the references related to the papers which are particularly on heritage conservation under library section. First of all, I would like to convey the apologies on behalf of Chairman Technical Committee 301, Professor Alessandro Flora, who could not join us because he is recovering from recent surgery he's underwent. So the dignitaries who are present for this particular lecture are the chief guest of this particular webinar, President Indian Geotechnical Society. The Technical 301 members, those who have registered, they have joined for this lecture. The speaker of the lecture, Professor Arun Menon, the faculty members, conservationists, practitioners, and dear students. Myself, Dr. Jitesh Chawda, on behalf of Technical Committee 301, I welcome you all for this lecture series on conservation of heritage sites. The lecture 2 of this lecture series will be delivered by Professor Arun Menon. Now, I request the chief guest of this lecture series, Dr. Anil Joseph, the President of Indian Geotechnical Society, to address the participants.
Hello, everyone. It's a pleasure for me to be part of this TC301 lecture series on conservation of heritage sites. It's a very, very important topic. And if I look in, it is one of the most active technical committee ISSMG has. It's quite dynamic, lot of activities happening. And in fact, the world needs a lot of development in the area of conservation. So I congratulate Alexander Flora and Jitesh Chawda for the efforts being put in, and all the technical committee members who are very active in different parts of the world for keeping it going. And this is one technical committee which is live throughout the year, and I congratulate the entire team for the same. And today we have a very dynamic personality, my good friend Arun Menon, addressing you all on a very, very important aspect, potential area of research and development in structural conservation of historical structures. Definitely, we need a lot of research and development needed to understand how our old structures, which are 5,000, 6,000 years, are able to perform. And now we are finding that the structures which are just about 50 to 60 years is getting dilapidated, and we have to start reconstruction, or even we have to go for demolition because of the unsafe condition of the structures. So this is very much essential to understand how at that in the history part they were able to achieve that, and a lot of research and development has to go into that. Arun has a great career. If you're looking at that, he started with an architecture, then went to do it MS in structural engineering, then another post graduation, then a PhD, and he's an expert covering the entire part of the globe. Like if you take Philippines, Myanmar, everywhere he has touched upon and has put his fingers, his hands to make sure that the heritage are kept intact. So it is a great opportunity for all the participants, and I am informed that more than 80 participants are already registered for the event to listen to that. I wish all the very best for the talk, and I especially encourage youngsters to take up this area of research and development in structural conservation. And of course, without structure, a structure has to stand, it need foundation. So foundation also have to be looked into, and since we are buried below the ground, it leads more attention to, especially in the concept of when we are trying to bring save the heritage structures. And I know that this is going to be a big opportunity for the youngsters to learn from Arun. And Arun, wish you all the very best, and congratulations Jitesh and the entire team of TC301 for bringing this webinar and continuously going on. I remember the first talk was delivered by Professor Guido Cottadi on July 10th, 2024. So keep working. We need a lot of these sessions to happen to keep our youngsters motivated in this area. Thank you and wish you all the very best.
Thank you very much, Dr. Anil Joseph, sir, to address the participants. Rightly said by Professor Dr. Anil Joseph. that we started this particular lecture series in 2024, and first lecture was delivered by Professor Goto Gotadi, and this time we have Professor Arun Menon from Structural Engineering Division from IIT Madras, and he's going to deliver on topic potential areas of research and developments in structural conservation of historical structures. Please note that this lectures which will be recorded, it will be uploaded also on YouTube as well, the ISSMGE virtual university. So in future, those who want to even refer to this particular video, they can access through our website also, and in the ISSMG virtual university also. Now I take this privilege to introduce the speaker, Professor Arun Menon. Arun Menon, Professor of Structural Engineering at IIT Madras, holds a first degree in architecture and PhD in earthquake engineering from University of Pavia in Italy. His research interests are in structural aspects of historical construction, earthquake behavior of historical masonry structures, earthquake resistant structural masonry, and earthquake risk assessment. He currently coordinates the activities of National Center for Safety of Heritage Structures under Ministry of Education sponsored Research Center at IIT Madras. He was an expert member of International Coordinating Committee for the UNESCO World Heritage Site at Bagan in Myanmar, and currently is a member for Expert Advisory Group International Conservation Committee for Wat Po UNESCO World Heritage Site in Laos. He has been involved in many conservation projects worldwide. Few of them are Rashtrapati Bhavan, IIM Ahmedabad, Madurai Meenakshi Temple, Konark Sun Temple in India, Tango Monastery, Wangdu Phondrongzong in Bhutan, UNESCO World Heritage Site Bagan in Myanmar, the Saint Sebastian Basilica Manila in Philippines. He is a member of Bureau of Indo Standard for Masonry Structure, Masonry, Conveyor of Panel for Masonries, Building Construction Practices Selection Committee, then Working Group on Revision of Seismic Standard for Masonries, Conveyor for Earthquake Engineering Sectional Committees, and Member Stone Selection Committee (CED). Then Technical Activities Committee of International Union of Laboratories and Expert in Construction Material, Systems and Structures in Paris. So with this short introduction, now I request Dr. Arun Menon to deliver his lecture, and we look forward to hear from Professor Menon on structural aspects and conservation of heritage.
Thank you
Over to
very
you,
much.
sir.
Thank you very much for the introduction. At the outset, I would like to thank ISSMGE and Indian Geotechnical Society for this invite. I don't think I have the authority to speak on geotechnical aspects, and therefore I'm going to face an audience that should be forgiving. I come from a structural engineering background, but I hope this talk can foster some sort of a collaboration between structural engineering fraternity and the geotechnical engineering fraternity, particularly on the safety and protection of historical constructions. With that, I'll share my screen and are you able to see the presentation in presentation mode?
Yes, we are able to see that.
Yeah, thank you very much. So at the outset, before I begin, I would like to thank Professor Flora, who sort of instigated me to speak on this topic, and I'm sorry to hear he's not keeping well and recuperating from surgery. I really wish him well. I would like to thank President of IGS, Dr. Anil Joseph. Thank you for the kind words and this invite. So the topic that I've chosen is potential areas of research and development in structural conservation. And when I say structural conservation, the word structural is present there, but it's more about a holistic conservation of the main resisting system of the historical construction, which, as Dr. Anil Joseph said, needs to pay attention to both structure and substructure. And that is really from two perspectives. We need to look at the historical construction and ensure that we are doing whatever is necessary to quantitatively and qualitatively address the safety of these constructions and work together to achieve their preservation. I have divided my presentation into three parts, a brief introduction, and then I basically move into what I see based on the experience I've had in a few sites over the last 15 odd years, are the possible areas of collaboration essential between the structural engineering fraternity and the geotechnical engineering fraternity. In this context, I would like to look at foundation systems in historical constructions and how they're very different from the modern constructions, therefore requiring a very different approach in first trying to understand how these function and then work on what can be the way these can be preserved. The second is really about calibrating numerical models when soil structure interaction is also considered. This is an aspect that is a methodology that is the calibration of numerical models is a strategy that's adopted to ensure there is reliability on the numerical model that you're working with for safety assessment. This is standard practice almost in structural engineering today, even working with historical monuments. But then when we bring in the geotechnical aspects into this, things can start getting complicated from a structural engineering perspective. How do we handle that? And this is something important which we need to address. The third is a very specific problem. This is specific to a certain monument, and it would be useful to have the thought process from the geotechnical engineering perspective to find solutions to the problem raised. The third is of deterioration of retaining earth walls. Now, retaining earth walls can be repaired, and there are many ways of many established ways of repairing deteriorated retaining earth walls when they are standard constructions or normal construction, ordinary constructions. But what if these are constructions which have very high sculptural value sitting on the retaining earth wall? That's again a specific problem, but I think there are many examples of this around the world. The final topic that I would like to touch upon is the traditional knowledge systems. In many countries, you have a very well-developed traditional knowledge system, ancient knowledge systems from the past. Very often, the present knowledge systems that we are trained in, the modern education in civil architecture, civil engineering and architecture, does not give us the possibility of understanding these traditional knowledge systems. In fact, we also overlook these traditional knowledge systems. But there's a lot of value in going back and trying to interpret these from the science and technology that we are aware of today. And finally, some concluding remarks, hoping that we can foster some collaborations on at least these topics that were mentioned, or as I said, these are from the perspective of someone working in the area of structural engineering. You might tell me, look, all these are already taken care of from the geotechnical perspective, and probably that conversation itself can move us structural engineers in the right direction in terms of preservation of historical structures from the geotechnical perspective. So the first one that I wanted to talk about is really the foundation systems in historical constructions. The way historical constructions have been constructed in the past, at least in a large part of in India or the Indian subcontinent, particularly with brick masonry and stone masonry, is really without a formal foundation, or what we understand as a foundation in today's context, where the superstructure is capable of transferring axial forces, not only axial forces, but also bending moments and shear forces to the foundation. Transfer of shear forces is definitely possible by the resisting frictional characteristics at the interface. But bending moments, that's going to be possible only if there is a positive connection between the superstructure and the substructure. However, in the ancient constructions, it was mostly a massive structure resting on a massive plinth. The raised plinth itself was really the foundation, and often there was nothing that qualified as a formal foundation beneath the plinth. Or in cases there was a foundation, it was nothing but the plinth, which was a buried plinth. What you see on the slide here is really a new construction. This is not an ancient construction, but a new construction following the ancient texts which are prescribed for temple structures. And what you see is the temple gateway in a Hindu temple. So in this construction, you can actually see what is the point that I want to make is how the foundation is constructed. So basically, after an excavation is made and a uniform strata is reached, the entirety of the excavation is filled uniformly with large blocks. And this is a complete stone masonry dry stack construction that we are talking about that is being built. And this is sitting on top of a massive stone bed. Of course, it is not just one block of stone, it's multiple blocks of stone which are assembled, and that forms the solid foundation or the raised plinth that I was talking about, depending on whether it is below the ground or above the ground. And right on top, you have the massive construction, which is right on top of this, you have the massive construction which is constructed and ensures transfer of the loads, particularly the axial loads, onto the substructure. But as I said, there isn't a positive connection between the superstructure and the substructure. As I said, this is current practice based on traditional construction techniques. This is a construction which is underway and began about 5-6 years ago. However, if one were to look at really ancient temples in the Indian subcontinent, you're looking at a region in the northern state of Uttarakhand, which actually is a highly seismic region. And if you look at the famous Kedarnath temple, the entire Kedarnath temple is actually sitting on a massive platform, a stone platform that's about 50 meters by 30 meters, a massive man-made stone platform, of course, in random rubble masonry, that then rises up to receive the main structure. The tests carried out at this particular site through MASW was able to establish the minimum depth of this sort of a man-made platform. So this has been the practice of construction of these massive constructions without thinking of the necessity of any embedment or positive connection between the superstructure and the substructure. The other way in which many of these structures have been built is make use of this terminology, if you've heard of this, called the sandbox foundation. And the sandbox foundation, actually speaking, is nothing but the excavation that is made and the excavation that leads to the removal of the existing earth and replacement of the existing earth with graded sand. Graded sand is compacted, and after that, the structure is constructed. Now, the edges of the pit are cleaned, and it is ensured that as much as possible there is no washout of the sand. It is on this sand that the superstructure, which is an entire construction in stone, is made. And this is again a prevalent practice in many parts of the country and in the subcontinent. This picture that you see on the slide is of the Kakatiya Rudreshwara temple, Ramappa temple in Telangana, dating back to the 13th century AD. And in the recent years, this has become a UNESCO World Heritage Site. And one of the attributes is the construction technology adopted at this site. So this is the UNESCO nomination dossier talks of the good earthquake resistance that this sand bed provides to this massive structure which is seated on top of it. So this is typically how the constructions in historical masonry, massive historical masonry constructions have actually proceeded. I would like to focus on this a little more based on an experience that we've had, which is in peninsular India, which is south and the peninsular portion of the country. A lot of historical constructions are constructed in the manner that you just saw with the sand bed. Many constructions, typical hypostyle halls that you can see, four pillared and 16 pillared constructions with a raised plinth are then constructed with a massive, with a heavy top at the on top of the pillars. These are normally dry stack constructions. You have stone pillars, then you have the corbels and stone beams. They're all stone on stone with mortar only used for leveling and not really as a binding material between the stone. And the stone in most part of peninsular India is very solid type of stone. Granite is used extensively in the southern parts of the peninsula. But all these constructions are almost dry stack constructions. As I said, in these constructions in peninsular India, which is not very earthquake prone, the connections are almost with the absence of any positive connections. It's just stone resting on stone, maybe with a little bit of a camber, just to ensure there is some help for alignment of these stones. So that's how these constructions are made. Of course, as I said, in southern parts of the country, we really don't have massive earthquakes, whereas there are portions of the country like in Gujarat or in the Himalayan regions where the earthquake activity is very significant. Constructions of similar nature in these regions have shown very poor earthquake performance, leading to total collapse of these structures and total loss of these structures. So in these regions of high earthquake activity, you do see situations where there are some positive connections with tenon and mortise joints, and in some cases, totally absent connections, or in few cases with iron dowels. So you have many types of variants here. And the question is always, even if you're looking at regions of low to moderate earthquake activity, what is the safety level of these constructions? And that brought us to study in peninsular India the type of constructions with only stone on stone contact and no positive connections, understand better the earthquake resistance of such constructions. If you're looking at a longer and longer time span, you want to ensure that they are resistant even to moderate earthquakes. So from that perspective, we did some numerical and numerical studies to begin with. After we did those numerical studies and got some insight into the behavior of these systems, we started doing some experimental work. And what you see here is a full-scale model that was developed at IIT Madras in our laboratory, which has a 3 meters by 3 meters biaxial shake table facility. So this is a 4-pillared hypostyle hall. You see the different components, the pillars, the corbels, the beams, and then the cantilever slabs. And on top of it, you actually have a terrace with lime concrete holding the structure together. These are typically proportioned by traditional masons or traditional architects, and the same were used for designing and constructing these structures. And we worked with one structure which was actually dimensioned to fit the size of our table, so that scaling effects can be avoided. Scaling and similitude requirements can actually be we don't have to use scaling of mass, and that is an important and time, which is an important way of working around this requirement, the similitude requirement. So in terms of the construction sequence, I just wanted to show you and then focus on the problem that I was really talking about. So they're all constructed in granite, and you have this base which the traditional architect requires that the entire construction is made on sand base. And now this, of course, on the table, we were able to put together only a sand base that was about 150 millimeters deep. However, in actual situations, these are much deeper, up to a few meters deep. So the plinth blocks are assembled over confined, saturated, and graded sand bed. You can see the sand bed, and then the plinth stones are placed. And in reality, this is what is essential for the builder, because it allows for leveling of the stone blocks right from the first level, and verticality can be ensured. And as you progress to higher and higher reaches of the monument, this really helps, because you are ensuring verticality of every element. There is no multiplying effect of out of plumb. So this is an important construction feature. But deep deposits of sand are known to have properties of filtering out or reducing the impact of ground shaking when they occur in earthquake prone zones. So you see the dry stack construction continues, and finally on top you have the lime concrete poured on the floor slabs, and then that's how the entire structure is constructed. So the real point is, how effective is this sand base? Of course, in this test, our focus was not on the sand base, on the sand bed, but more on the structural behavior of this construction. And therefore, what is important to understand is what is the kind of role played by this sand bed in terms of the ground excitation reaching this structure. So that's something that requires some amount of inquiry. So this work was presented in a Geotechnical Engineering for Preservation of Monuments and Historic Sites in 2022. And so if some of you are interested, you could look at the details of this publication, which has all the tests. So the test was conducted, and you can actually sorry. The test was conducted at our laboratory, but it had only this minimal sand base, and we kept scaling the ground motion records, and of course found a mechanism which was quite well predicted numerically, as well as using an analytical framework. But in all these cases, it completely ignores the presence of a deep sand bed. Of course, as I said, on the table, there was a very shallow 150 millimeter sand bed. But if there were to be a deep sand bed, then does it have an impact on the ground shaking in the transfer of the ground motion records onto the structure itself, is a question that I don't think is answered quantitatively. So this is, as I said, a numerical part and an analytical part, which very well captures the structural behavior. However, this is completely ignoring the presence of the sand bed and what the sand bed can actually do to the entire system. So in terms of the type of foundation systems that you see in these historical constructions, particularly those with this deep sand deposit on which the compacted sand deposit on which the main structure is constructed, an important question is there a role played by a relatively deep artificial sand bed? Mind you, this is not the original soil. The original soil is completely removed and replaced with graded river sand and compacted. On the seismic response of particularly dry stack masonry constructions, is there a significant role that this type of a construction plays, is something that needs to be understood. But for this, we really need a collaborative exercise. The same, not only dry stack stone masonry constructions, but also for massive masonry constructions like the temple gateway that you were seeing, the massive multi-storied construction is also built on a sand base of this nature. So the question is, how does this really affect the earthquake response or the earthquake input? Is there anything that is modifying the earthquake input? If so, how much? And if so, how deep must this be? So if this is really happening, what is the minimum depth of such sand beds to be able to alter the ground shaking parameter? I think this is something that is of interest and we should be able to look at. Let me move on to the second problem that I think we still have not much of clarity on, at least in terms of guidelines, at least in terms of what should be done and what is the correct approach to be adopted. Whenever we do structural modeling, we begin with a good geometrical model, and there are many ways today. One could scan a structure and then convert the 3D model from the scan into a finite element model. And the processes from 3D scan to a 3D geometrical model, maybe in programs like Rhino, and then importing these two finite element analysis software to carry out meshing, so that you have a model that can really start doing structural analysis for you. The workflow is pretty well understood and adopted more or less everywhere in the world. But how reliable is the numerical model that you're working with? One has to resort to calibration of the numerical model. And when you calibrate the numerical model, you need to calibrate it to some experimental test data. And it is in that context that ambient vibration testing comes off as a very important sophisticated tool, where you're actually measuring the response of the structure to vibrations that exist in the region, in the environment. And these are due to wind, due to traffic, due to people moving around, and these are very small vibrations, and you're really not subjecting the structure to any forced larger vibration. Hence, since you're only working with measurements of the response on the structure and you're not inducing vibrations artificially, we typically call these as output only methods, where you're only measuring the response, and that is sufficient to characterize. You consider the ambient vibration to be white noise, and you characterize the dynamic response of the structure. There are also methods where you have an input-output method, where you actually have to shake the structure and then measure the response, and you can measure the input and measure the output and then get the dynamic characteristics. Of course, those are more sophisticated systems and may be warranted in the case of some types of historical monuments, given their size. But ambient vibration testing works quite well. So in this case, when we work with ambient vibration testing, we instrument the structure and measure the vibrations. Now, mind you, when we do that, we are really looking at the structure sitting on the soil, structure sitting on the structure and the substructure sitting on the site. And if that is the case, the response that we get is really not decoupled as structure's response from the site response. It is a combination of effect of the site response and the structural response that we are actually able to measure. Now, what is the standard practice? Once we make these measurements, we take these measurements from the ambient vibration testing, and there are ways of carrying out what is called dynamic identification and identifying the modal properties, and which you get the frequencies, the mode shapes of vibration, and you use that information, which is actually an information coming from the soil plus the structure system, to calibrate a model which may be sitting on a fixed base assumption. Of course, if the fixed base assumption is not an acceptable assumption, you would have to go for something with the soil structure interaction model. So this, in the process of calibration, we pick up one of the structural parameters, material parameters. It may be material parameter like the modulus of elasticity of the material, and keep changing the modulus of elasticity of the material till we see a convergence between the recorded dynamic behavior and the simulated dynamic behavior. That is how typically model calibration is carried out. So we have the numerical model with, let's say, fixed base condition. I have measurements on the structure, and I take the measurements on the structure, do dynamic identification, get the mode shapes, mode frequencies, and then check what I'm getting from the numerical model. If there's a disparity between the two, I calibrate the numerical model with one or two parameters, maybe work with one parameter like modulus of elasticity, till I have matching results between the modal properties of the actual structure from the ambient vibration testing and the numerical model. And then I believe I have a calibrated model which I can use for any type of analysis that should give me some reliable results. However, the question that I'm raising is, if you have ambient vibration test results from a structure which is actually sitting on its foundation and the neighboring soil, then in reality, the data that you're getting is of the entire system. Now, one has to be careful how that data is used to calibrate a model which is sitting on a fixed base system. So the guidelines on working in such a context are not very well established. So this is, you can see how the instruments are placed at different locations, and the test is conducted, data is used, and with this data, we calibrate the model. And the finite element model, as you can see, in this particular case, we had a finite element model with the entire soil also modeled, and the 3D model of the structure on top of the soil. And the intent was, for once we've calibrated the model, we actually will be able to carry out some modeling to understand vibration levels that are caused by construction activity in the neighborhood. So this is how the procedure works, and then you do this calibration, and then you look at the fundamental modes of vibration between the dynamic identification from the ambient vibration tests and the numerical model itself. Therefore, the questions that I have, if you're really looking at a numerical model with soil structure interaction, then how are we going about, how do we go about the calibration process, especially with finite element models where you might have the soil, the surrounding soil also modeled in the finite element model and the structure, or you replace the model with the soil model with springs for a three-dimensional finite element model of the superstructure. So key questions to be asked here is, how should an integrated soil structure model be updated based on ambient vibration testing? Are there some thresholds to say I can completely ignore the soil? Yes, maybe that part of the literature is quite clear in where should a soil structure interaction model really make a difference. But in case I have to work with the soil structure interaction model, then how do I go about doing this based on ambient vibration testing for model updating? And then if I'm doing that, which structural parameters should I pick up? Please understand that elastic modulus of the material is a proxy for one structural parameter that can be used for um, one parameter from the structure that can be used for model updating. I change the modulus of elasticity, I can change the period of vibration of the structure, but it might not necessarily be completely due to the material modulus of elasticity. It could be due to other things, which may be due to connections and the flexibility of connections in different parts of the structure. So if I'm using modulus of elasticity as a proxy for the structural parameters, what should I do for the geotechnical parameters, and how will I achieve a simultaneous calibration of structure and geotechnical parameters for simultaneously doing a model updating to create a reliable model. So this is a second thought that I have, is somewhere strong collaboration between structural and geotechnical engineers is essential to have a better understanding of the right procedures to be adopted, valid procedures to be adopted as we move forward. The third thing, as I said, is a very, very case-specific situation, and that is and that is to do specifically with a monument, which is again a World Heritage Site in Orissa. It is in the eastern part of peninsular India, and it's a massive construction called the Jagmohana of the Sun Temple of Konark. However, this is structure that you can only see from the outside. You cannot enter. The entry points are sealed off. There is documentation, very interestingly, right from the period of construction on how this was constructed, and there are drawings. And what is very clear, also looking at the ruins at the site, is what survives today is only this structure. If you can see the pointer, is only this structure, the picture that you saw in the previous slide, whereas the massive structure that you see right next to it, which is the main sanctum sanctorum structure over the sanctum sanctorum, has actually collapsed. This structure is much smaller structure, and therefore the drawing is not very, this ancient drawing on palm leaf is not completely accurate. Probably it's a reproduction over time and from the 17th century, and probably some distortion is there. So we're talking of this massive structure in the center. There are paintings of the various stages of collapse of these structures from the 19th century. Here you can see a picture on the left from 1848, which shows a remaining part of the massive structure behind and the surviving Jagmohana. You can also see a photograph from 1890, which shows the pile of debris from the collapse of this. In fact, there are written documents that mention the initiation of collapse in the initial years after the construction, which is in the 13th century. So right from that period, there has been some structural distress to an eventual collapse by 19th century. What survives today is this massive construction. And however, what really happens is around the same time, there is evidence of structural damage happening inside this structure as well, inside the surviving structure. So you can see an interesting painting from 1812, which shows that there are parts of the structure which have actually already collapsed. What you can see is an entire inner inner wall of the structure has been damaged, and there is a historical record of a massive sculpture from the main structure collapsing onto this structure and impacting it at the exterior of this wall, which has led to the collapse of stones, as you can see in the painting from the interior. There is also evidence from the construction methodology of these massive constructions from the traditional knowledge systems that there should have been 4 massive pillars inside. However, this painting does not record the presence of those 4 massive pillars, implying they might have collapsed or implying there was a deviation from the original construction of such structures when it was finally constructed in Konark. So this is the last known record of what the interior looked like. What happens after is in early 20th century, a decision is taken, and you can see an edict which basically declares by the British government from the province of Orissa that to preserve this superb specimen of old Indian architecture, the interior was filled in by order of the Honorable Lieutenant Governor of Bengal in 1903 AD with sand. So the entirety of the interior was supposedly filled with sand after sealing the 4 entry points into the structure, after introducing a wall, internally a wall to hold the sand, and then filling it up to the point of the wall, and then starting the fill from the top, because the point through which the sand was then poured inside after sealing the doors is recorded. So the drawing that you see on the left is a drawing from 1903, and this is an as-built drawing, meaning all the engineers who have signed there at the bottom have actually recorded that this is how the construction has been sealed with sand. So the record says that the entirety of the interior was filled with sand, and all openings, there are no other larger openings to make an entry into the structure. There are, of course, small air vents. However, all the main entry points are completely sealed, and the sand is the purpose of the sand was that falling stones are prevented from moving inwards. They are constructed by what's called the corbelling technique, and so the sand should work to resist any movement of these blocks and maintain the structure, so that people can at least see this marvel of a construction from the exterior. However, many years later, in the 1960s, Archaeological Survey of India, which really takes care of this monument, wanted to understand what is the situation, and there are many evidences of possibly the sand not being right up to the top, holding up the ceiling, and therefore a lot of investigations were carried out to understand where is the level of the sand, and by introducing a camera through one of the openings, it was detected that the sand fill is several meters below the ceiling itself. Now, how did a structure whose sand fill was taken up right to the top by filling finally from the top result in a structure where the sand fill has now come down by almost 13 meters? The level of the sand has actually come down, and today the sand is 13 meters below the apex of the structure. So this is puzzling, and there isn't a complete understanding of where all the sand has gone, or is it just compaction of the sand? Was it really compaction of the sand, or is there some crevices through which the sand is actually escaping? But escaping where? Because you've sealed all the exit points to the structure. So this is an interesting situation, and currently the status is that a lot of studies are being carried out. And the last 20 years, a lot of studies have been undergoing on the structure, primarily to understand whether if the sand has actually come down, then what should we be doing? Should we fill it up with sand again, or should we try and remove the sand and gain access and then try to consolidate the structure so that people can actually go inside and visit the structure? Currently, the pilot project to gain access into the structure is being carried out by the Archaeological Survey of India. Hence, it's a very interesting project. Now, what I wanted to immediately focus on is the sand itself. Now, this sand, we were actually able to collect sand from two different locations inside the structure. And we also wanted to understand where did they get so much of sand, although it is recorded that it is river sand that is being collected. So of course, there is evidence that it is river sand from a nearby river called the Chandrabhaga River. But it's also very interesting to see that this Chandrabhaga River then feeds into the sea, and the sand collected from these three locations have quite similar properties. They're all poorly graded sand, and what's very interesting is the angle of repose is very shallow. So it's about 17 to around 17 degrees of angle of repose. What we were really concerned about is if we were to start creating an opening into the structure, will we see sand gushing out? And whether that is a problem at all, because we were planning to open the structure. We are planning to open the structure at a level below the top of the sand. And therefore, one question was, when you start opening, are you going to see sand gushing out or not? But with this very shallow angle of repose, that fear is really not there. So some of the key questions around this structure, around this very case specific problem is, what has happened to the sand? If the sand, it is recorded that the sand was filled up right to the top to hold up the ceiling of the structure, which was actually caving in. Where did the sand go? Why is the sand getting consolidated so much? And it's quite a volume of sand that is today. There's a void. Creep, is it a possible direction to think about? Primarily, the issue is we're talking of something that has been carrying its own weight for the last 120, 121 years. So is it creep? Is that feasible? Do we know what is the level of creep in sand? Is it expectable scenario? Second, can this be an explanation for the subsidence of sand, or do we have some other explanation for the subsidence of sand? Of course, compaction only has been possible to a certain level till which people were able to access, beyond which sand was only poured inside. So again, there are open questions about how did the sand even come down so much if the structure is completely sealed. I'll go to the last two problems, which are much smaller in terms of how the problem is conceived, at least in my slides. This is a very famous, again, World Heritage Site in Gujarat, in a place called Patan from the 11th century. And this is a complete subterranean structure. And these were water retaining structures. It's actually a step well. You can, this is the ground level. You can walk down into the step well and access the well. And these wells are really, the well at the end is really deep. You can actually, even during summer months, ensure that some amount of water is available to travelers who are going across from place to place. This becomes a shaded resting place, and there is a possibility of finding water in these step wells. And the whole of these northern plains are actually spotted with these very famous constructions called step wells. Now, if you look at the walls of the step wells, these are all the massive retaining walls of the step wells. These on sandstone have very exquisite sculptural quality. This is something that is the quality of the stone and the quality of the sculptors who have actually worked on this. What is the problem that I wanted to focus on? If there are issues with the retaining wall, and the issue with the retaining wall is not so much about the movement of the retaining wall, but really about the movement of moisture. There is movement of moisture to the inner surfaces, and of course with movement of moisture you have a lot of efflorescence, and the surface embellishments, which are some of the most exquisite carvings in sandstone, are actually getting affected today, 700 to 800 odd years later. So what sort of an intervention needs to be carried out? Trying to coat with membranes, silane or siloxane membranes, these beautiful sculptures is possibly not an option, because you'll end up blocking the movement of moisture. Are there any site level interventions that can be carried out that can actually, what measures for protection of these sculptures for retaining walls should we be thinking about, if it is clear that it is the moisture movement and the efflorescence through these retaining walls that is really affecting these structures? The last thing that I want to touch upon is the Indian subcontinent is very rich with traditional knowledge systems, ancient texts that really record how structures were planned, structures were designed, structures were built. That's only in the science of building, and this is actually a sort of available in all other disciplines like medicine and metallurgy and astronomy and so on. So with respect to the building sciences, it's very interesting to see the level of detail to which materials are described, characteristics of materials are described, and tests for soils when sites are selected are even prescribed. So this is a couple of examples here, and I have found a similar sort of a text being referred to even in Bhutan, where the construction of monasteries or construction of even residential quarters or palaces are regulated by these texts. So one of the texts which is really written down around the 5th century, we start finding written manuscripts on these regarding these, but prior to these they were by word of mouth. So one of them is Mayamatam, and there's an entire chapter that deals with soil investigations, site investigations. The 3rd chapter deals with site investigations. It deals with testing of the soil and selecting, the type of soil which is fit for a certain construction and unfit for a certain type of construction. You have other famous books. Kashyapa Shilpa Shastram is another one, and it's very interesting. Couple of tests described is one where 1 foot by 1 foot pit is created at the site. The soil is taken out, and after a while, the soil is put back. When you put back the soil after a while, if there is more volume available to fill soil than the original volume, then the condition is the best condition that you can work with. If you have a situation where it just fills up exactly, it's a medium situation. And if you have a situation where you've put the soil back, but now there is more soil to pack into this cavity, then it's considered not the best site to work with. There's another test where once the pit is made, you fill it with water, and then you take 100 steps away from this point and come back to the point. When you come back, if the water has just remained there, it's considered to be an acceptable site. But if you come back and there is almost no water left, then it's a site that you don't want to work with. So these are very interesting scientific principles based on which the building, the art of building has been based. These must be open to inquiry. It is important to understand what is the analogous practice today? What is the scientific explanation for this today? To what extent were our ancestors right in the methods that were adopted? And that's the scientific inquiry that we can actually delve into with respect to these ancient texts. It can give us some very insightful knowledge which we can apply for today's cities, today's constructions, and understand how to create continuity, how to create a sustainable living environment. So that's really where I'll stop. I just want to say that structural engineers and geotechnical engineers, when we deal with buildings, it's always like a relay. I do my part and then pass it on to the next person. The next person works, and we all work in silos. We generally try to work in silos. You give me your answers, I'll take it and go to the next stage, which is okay. But you can drop something in the relay, and the speed of the relay can be limited by the slowest person or the fastest person. And so this is a good option, but the best option is what collaboration will look like. So if you've heard of the three-legged race, where two people are tied together and have to run together, it's not about how far. It is really not. It is about completing the race and reaching there. You can't run very fast, but you'll have to accommodate the other person and ensure that you reach fairly fast, but carrying the other person. And I think if we have a healthy collaboration, an important dialogue to understand from a structural perspective, and from a geographical perspective, preservation of our historical sites can happen in a more holistic manner, not in a disconnected manner. I'll stop there and take any questions if there are any. Otherwise, the recording is available, and you should be able to contact me if you have any clarifications. Thank you.
Thank you, Dr. Arun Menon, for giving a very much good insight about the structural aspects of heritage conservations. So now this forum is open to question and answer. So the participants, those who have questions, please feel free to ask the questions. You may also put it in the chat box if you have any questions. I'll read to the speaker. So if there are no questions.
Yeah, thank you, Arun, for the excellent session. It was very informative and a lot of things to be done. I have a question. So we have seen that in most of these old buildings, we have timber pile, and we have seen that all timber foundations being provided. So how, because now the timbers are not that available. So when we are going for this heritage revamping, what sort of, how, whether we should use the same similar material, or can we, because I know the Ayodhya temple, we didn't use steel because of the long time problem. So what will you suggest? And well, if the availability of the material is not there, what we should go for as a new foundation system on that?
It's a very challenging question, because it also touches upon the philosophy with which we deal with historical constructions. So as much as possible in an archaeological monument, the attempt is to work with like for like. So if there's a deteriorated material, like stone or lime mortar or whatever, the attempt is to use similar materials, so that the structure is in equilibrium with a certain type of materials and certain structural load path. You're not deviating too much from that. But there are also contexts where it has been found that some of these traditional systems may be inadequate, also maybe due to some new environmental factors. And in such conditions, an informed decision can be taken to go with a different structural system. So it really has to be case to case. And there are instances of historical constructions where a reinforced concrete foundation has been introduced, although the original structure, I'll give you the example of St. Mark's bell tower in Venice, which originally had timber piles, because many of the constructions in Venice are sitting on. I mean, the whole of Venice is sitting on timber piles. Whereas the St. Mark's Tower had collapsed once, and when they were reconstructing, they actually adopted similar approaches. But then a recent intervention in the last 2 decades ensured that the foundation problems are tackled more effectively by introducing a reinforced concrete ring beam and a foundation system. So it is really case to case. Sometimes it may be because of changed conditions, the traditional approach may not be adequate. Where it is feasible, it may be useful to do it in the same process if things are have remained unchanged and material is available and the knowledge to do it is also available.
Thank you very much. Thank you very much for answering that. I have this question doubt with me that how we will manage that. So thank you very much for explaining on the note. Thank you.
Thank you. Thank you.
Okay. Is there any other questions from the participants? Okay. So if there are no questions, then we can end the sessions here. So I really thank Dr. Arun Menon to cover upon, the 5 important aspects, that is foundation systems, then calibration of numerical model with soil structure interactions, then effect of sand filling in the structures, then deterioration of the retaining earth walls by considering the case of Rani Ki Vav, the interpretation of traditional knowledge systems, and how it can be related to the present practices what we are following, which is based on mechanics based. So I really thank Professor Menon to to ignite this particular topic to all the participants here. And in future, those who have want to collaborate and they want to contact Professor, they can reach to Professor at the email details are available at the website of IIT Madras. Now I thank Dr. Anil Joseph to spare the time, the President of Indian Geotechnical Society, for this particular webinar series. So, and all the participants who have joined. So I thank you one and all.
Thank you all.
Thank you. Thank you very much. Thank you, Professor Jitesh.
Thank you. Thank you very much.
Yeah. Bye-bye.
Bye-bye.
Yeah. Thanks a lot.